Hey, welcome. Thank you for attending this event. I'm very happy. I'd like to introduce the speaker. Okay. Before I do that, I just want to introduce myself. My name is Hua Chen. I'm the faculty in the biology programs. Okay. Another hat I wear is kind of the research fellow for the Office of Research Sponsor Program. So, and today I'm going to introduce Dr. Hong. I think he's going to speak. Come in. Yeah. So, Dr. Hong actually have very impressed, very long CV. So I'm not going to cover the long CV. So I will simply kind of go ahead to introduce. He got his PhD from applied mathematics from Auburn University, which I spent 2 years there. So, and he also has 2 math degrees. One is actually math degree of computer science from UIS, and the second math degree actually from I think compute mathematics from the University of Science and Technology in Beijing. So, Dr. Kong's research focused on differential equation and also machine learning. One very interesting point, I think, because her research focused on spatial dynamics, including ecological system and human society system, which I'm very interested. Okay, so he's going to give a talk. The title of his talk is "When Differential Equation Met Machine Learning, What Happened?" Okay, all yours.
Thank you for the introduction. Yeah. I do have one piece of slides for you, Dr. Ken, about application in some ecology. So, so yes, thank you for coming for this rainy afternoon. So, at the end of this 1 hour, I hope you can brush up some of your mathematics, whatever, calculus with me today. And the title is "When Differential Equation Met Machine Learning." You can basically tell this is interdisciplinary research in applied math or computational math and AI, artificial intelligence. I'm fortunate to have several collaborators, including very hardworking, talented students. I see a lot of familiar faces here. I know some of you guys are working with me right now this semester. So first, big thanks to the Office of Research and Sponsored Program to award me this competitive scholarly research grant in 23-24 to enable me to hire 2 students as research assistant. So Chris is one. He's a junior this year for math majors. So actually, Chris has done some fantastic job. He used a deep learning method to analyze and simulate some complex system. And we have completed 2 manuscripts, and 2 of those are under review in some math journals. I believe the second paper we has been received some favorable review from the Journal of Mathematical Education in Science and Technology. And I'm pretty feel good about the first paper actually. So, and Chris also present his research in multiple conferences, including the STARS last year and also the Chicago Area Undergraduate Research Symposium in last year. And he also present his research at a mathematical association, which is a test.
Oh, okay.
Looks like it's good.
Oh, yeah, now it's good. Now it's good.
Oh, okay.
The icon up there.
Okay. Can you hear me right now? Oh, no. Let's see which one.
Run it through the check my audio devices prompt there and it might fix it.
This
Like we
one?
did last time. Run it through that.
Okay.
It's,
Okay. Can you hear me right now?
yes.
It looks like, hey.
Okay, great, great. All right. So what I mean is Chris. So, so I think Chris is actually Chris this year he had done some other research with me, and I'm very glad to have him in my lab. It's a screen's program. Okay. All right. Everything looks good right now. Yeah. Also, Anthony is the second student I hired as research assistant last year. Actually, he did a novel hybrid AI method to solve some classic differential equation and even partial differential equation. There is some application in biology and mechanical engineering for the equation Anthony solved. He presented in STARS and also our one of our paper has been published in a proceeding of a conference in Japan, and it's also appearing in IEEE. So let me put this in context, what I'm doing here. So there is a growing intersection between computational math and AI. Basically, is how we use machine learning or deep learning to accelerate the computing. To accelerate computer means how to solve some equation system for us, to analyze some ecological system for us. So we use AI method. So this mingle between AI and computational math is really something I'm deeply interested in. So in the past 4 or 5 years, we with my collaborator, including students and US colleague, we have done some work here. So today I'm just going to just scratch the surface of what we have done and give you an overview. So this is outline AI, right? So we have two parts, AI and differential equation. So what is AI? So actually, right now, AI gonna be AI takes the world by storm. Everybody talk about AI. So actually, AI research has been experiencing some up and down. So sometimes we call it AI summer and we call it AI winter. This terminology is not new at all. So actually, this term is coined by a mathematician 70 years ago in 1955. And at that time, AI is not trainable. So that's why there is at least 2 winters between at that time until now. And I'm going to go over a little bit of history of AI and how you use AI to compute the system. And then I move to the second part, differential equation. What is differential equation? And in the application world, it's called dynamical system. And there is some model in epidemiology and also in ecology. And finally, I will introduce what kind of research I'm doing right now with our colleagues and with students. Actually, I'll be here, so he's doing some work, which is SEIR model, is a type of epidemiology models we are doing. Use AI hybrid method. All right, so if you ask any computer scientist who is the most influential scientist in computer science, actually, the chances are you heard this name. Alan Turing. He is a British mathematician. At that time, there is no computer scientist yet. The mathematician and computer scientist. And he is widely considered to be the father of theoretical computer science. There is a war after his name, and which is also viewed as Nobel Prize of computing. So he initially gave us he asked a question, very important question. In his paper in 1950, the paper is called Computing, Machinery, and Intelligence. In the first sentence of that paper, he said, I propose to consider the question, can machine think? It's just one question, just changes it, give us a direction. Maybe it changes the human life So can machine think? At that time, think about that time, 1950. But machine can compute. 1 plus 1 equal to 2, right? Can machine think? This is a very forward-looking question. Actually, in that paper, he not only asked a question, he also gave a test. Later on, it's called a Turing test. In the test, he proposed if a machine can pass this test, we say this machine it can think, has intelligence, or has conscious. So what's the test? Basically, this test involving 2 humans and 1 machine. One human is an evaluator, human C. He gave a machine or another human a test by written. He gave a message. Written message. I gave you a test. Try to solve it. Okay. You don't know which one is machine, which one is human. A/B test. Think about statistics, right? You don't know which, and then the machine can finish the test and get back the result. If the evaluator C cannot tell which one is done by machine, then we will say this machine win the test. Okay. Think about the ChatGPT right now. Large language model. Can you tell the difference? It's hard to me to tell the difference, right? So for certain tests, definitely, large language model has passed this test. For certain tests, I'm not saying all the tests, right? So yeah, so this simple idea gave the birth of AI. However, this terminology, artificial intelligence, does not appear until 5 years later. So there is a grant proposal. It is written by John McCarthy. He's a first-year assistant professor in Dartmouth College. This is young man here. So he in his proposal, he's trying to apply some grant money from the Rockefeller Foundation. He's trying to give a grant proposal. In that first sentence of the grant proposal, he wrote this: we propose a 2-month, 10-month study of artificial intelligence be carried out during the summer of 1956 at Dartmouth College. Since then, this term, artificial intelligence, is appeared in human literacy. Okay, this is the first time they coined this word. And I like running grant. I have trouble to give the budget. So I go back to orange.
You get way more than them.
Yeah, but you can see that they ask for about $13,000, but they only get half of them, right? So I think this is a pretty well spent $7,500. Right? All right, so AI, as I said, AI evolved over time. There is a phrase it's called symbolic AI, which is John McCarthy spent a lot of time to do. This is in 1960. And then they move to expert system. Expert system is more has application in medical and financial field, and in 1980. But I'm not going to talk about these 2 fields because they have a lot of promising application, but they do have a lot of limitations. So now we talk about AI, ChatGPT, is because of the development of neural network. Okay, I'm going to just talk about the history of the neural network. So basically, neural network is how we build a mathematical formula for our brain. Our brain has nerve cell, neuron, right? So how we build a model for neuron? So human probably have more than 85 billion neurons. So how we build a mathematical model to do it? So model, when we do the model, we're gonna see the original nerve cell, right? This nerve cell. The characteristics is this cell has 2 ends. One end have dendrite, it's called dendrite. The other end is called axon terminal because this trunk part is called axon. So basically, scientists find out there is a electricity and chemical signal pass from one end to the other. And then our billion neurons connected together. How we model this mathematically? It's very challenging, right? So let's start from the simple thing. So the first people model the neuron is Frank. He's actually not a mathematician and computer science. He's a psychologist. He's Frank Rosenblatt. He used a mathematical formula to model the neuron. So basically speaking, is you have dendrite. So each dendrite we call this as input layer. Actually, there is because this system, because the signal pass starting from here, right? So we use each xi, maybe for example x1, to simulate the signal passed through each dendron. Okay? So each dendron, the simulation is different. Maybe they have different lengths, right? We use a weight to weigh this out. So that's going to be x. Use sigma xi times wi. Or wi times xi. Weigh this out. We plus some constant bias. And also, scientists also notice the signal going to pass through is not linear at all. It's sometimes weak, sometimes strong. So you use an activation function, which is a continuous but not a linear function, to boost this up. Okay, this gives us output. The input is x, the output is y. Use this very simple formula and can model one neuron. Okay, you will stack them together. This is going to be our human brain, right? So this is the most simple version of the human brain. So. But at that time, you can see this actually is Frank Rosenblatt himself, and he is actually this is his neuron computer. You can see that it's very, very complex. And also the computer, we don't have, there is no data there. There is no, even no, the hardware is still not there yet. So he just gave this theoretical theory, but this cannot be trainable, okay? It cannot be usable. So, so with the developed modern computer, internet makes all the data available. Now we have the potential to draw more attention. So here is some snapshot of the development of AI. Like first people stack them together and as MLP, which is multi-layer perceptron. And then this actually AI really have some power more than human, which is they can beat the chess and the Go players, you know. And now you run ChatGPT. Okay, so in my opinion, there are three most important components to why AI develop as this way. First one is algorithm. So we should have algorithm to train the data. Second is the data. We should have a lot of data to train the model. Third is going to be this how you do it, right? Software and hardware you have. And the algorithm part is algorithm. Right now we talk about this back propagation. Is also not new. It has been studied by some scientists in Finland. He studied this method in 1970s. And it's popularized by three other scientists in multiple applications. And actually, these three computer scientists all received the Turing Award. And especially the Geoffrey Hinton, he received the Nobel Prize last year in physics. I remember Dr. Chen has a talk about their results, right? So, and the data. Okay, the data is right now we have a lot of data, and I do have a pop question for you, quiz for you. How do you think how many data are generated every day by human? Like I'm talking here, right? There is Zoom here. I generated some data. There is if I use the unit as terabytes, there is 400 million TB each day. So that means our model could be 400 TB better, right, each day. So and also the hardware, software, NVIDIA, whenever he's the top #1 company. Why? Because there's GPU can train a neural network. Jensen Huang don't know actually his hardware can train a neural network until somebody tells him, because his GPU typically is just for the graphic processing, right? Actually, it happened to be could be trained in neural network. Sometimes it's an accident for success. All right, so let's move to differential equation. And what is DE? I want to start a quote from Alan Turing. This name will appear later. Turing said science is a differential equation. They say, I personally I personally don't think this is overstatement because you think about the Newton's law, you think Einstein equation, all those kind of physical phenomena, as long as evolving with time. We live in a time space, right? They're gonna be could be written in some way, in some sense, as differential equation, because differential equation or dynamical system describe and analyze system changing over time. So you think this is pendulum movement, this is very, very simple one. And if you can get, actually this could be describing a differential equation. So if you know the angle, if you know the length of this rope, if you know the general gravity, right? The gravity constant, you know that, right? So we can form this equation. After I solve this equation, I can predict the location of this ball as long as you tell me the initial, where is this ball located, right? I can tell at the 2 seconds later, where is the location of the ball. So that's the magic of differential equation. Use very simple and few variable to describe the initial phenomena. Only have how many? Theta, G, L, right? Couple, right? 3 or 5 variable or parameter you call it if you want, can describe this phenomenon. So this is for Dr. Chen, actually the application for ecology. So this model is a local Batara predator and prey model. This model actually represents for, we have 2 animal species, the relation is prey and predator, that computation. So we can simply model this relation by this mathematical differential equation, by these 2 equations. X represents the density of the prey. In this case, is it hare, and Y is the population density of the predator. It's links, right? So the left-hand side, don't let this term fool you. Left hand just tell dx dy will just represent the time, the change of the population change over time of the hare. Say yesterday we have 10 hare, today we have 12. The change is going to be 2, right? Just use today's number minus yesterday's number. That's the change. This is given by, they have some parameter here, alpha, beta, gamma, delta, and gamma. Alpha represents the birth rate of the prey. And beta represents the death rate of the prey contributed by Y, contributed by predator, by the lynx. Lynx is going to be kill some hare, right? So the rate is going to be determined by lynx. And also we can think about the relation between them and the birth rate of the lynx. If there is enough food, more food, the birth rate of the lynx should be higher, right? So that's impacted by the number of Y. And the death rate of Y is written by God. Okay, we can solve this one. We put it in the MATLAB, whatever, Python. You can end up. This is a simulation of the population, and we can tell. We can just focus on the radar curve here. Initially, there is a low population of the lynx, right? It's going to be increased. Well, when the prey population at the top point, which is you have a growth birth rate. Okay, so there is no. This is a simulation. This is the real world data. So you may think there is no way people can find all the exact population for these 2 species. However, this data is from a Canadian company, fur company. They're selling these 2 types of fur. They collect those data. This is from actually 1845 to 1935. It's 1845. We can tell the real data, the real fur selling is coincident with our simulation. It's quite similar. Okay. This is the SIR model. This is some application in epidemiology. So typically speaking, in a high level, let's see how we model this. Okay, think about in our classroom we have 20 individuals, right? Myself get a contract with COVID or flu. I'm talking here, so I spread a lot of disease, right? Let's starting in this room only. Population gonna be fixed, gonna be closed, no migration. Nobody allows to come in and get out. Okay, let's try to model the dynamic of this disease spread from 1 to 2%, how people gonna be get infected, how much time they're gonna be infected or get recovered. Okay, so typically all the human body are gonna be separated as 3 compartments: suspectable and infectious and recover. So in my model here, there is a lot of limitation because I have a lot of consumption here, condition there. This model, because I told every population is closed, we have a constant population. People are well mixed. Not just I talk here. Everybody should be talking in 10 minutes. How about that? Everybody have a chance to spread the disease, all right? So that is me, all well mixed, no social structure. Okay, there is no elder people, there is no younger people, there is no newborn. Everyone have the same contract rate. And no mutation, and disease, no mutation in 1 week, right? And there's no reinfection. A lot of condition which is make this model almost unuseful, not useful, because you have a lot of. Why we do that? Why you model it, right? So actually, I like one quote is called "All model is wrong, some is useful," because we'll get some insight from the model. We can make this more complex. We can make it has social structure. We may have to change the infection rate later on. This is just a foundation model. Okay. So again, so from this model, there is 3 variable and several couple parameter, 2 parameters. So one number we are really interested in is called basic reproduction number. It will be written by this way. Beta here is infection rate. 1 people can infect how many people? Gamma denominator here is recovery rate. 10 people, 1 dead. Maybe 10 people can recover 3 of them. Maybe 2 of them have a long-term complement, right? Something like that. So they have this number give us the reproduction number. If this number greater than 1, this disease will be coexistent with human. If this number is less than 1, this virus gonna be die out. Okay, so just a simple simulation here. If this is over is 2, we can see that this is quite close to 0, but it actually is not equal to 0. This red curve represents the eye infection. This is something we are really interested in because we flat the curve in COVID, right? Flat the curve. This curve, infection curve. So another example about this R0 in the COVID-19, in the initial COVID in Wuhan, this number is about 3, which is you pass 3 people by infection. And in the very end, in the Omicron strain, this number is go up to 8. Okay, that's why it's very hard to kill this disease. Okay, so I can use my half time to talk about the history. So what's the relation between DE and machine learning? Okay, why they could be mingled, right? So do we have a common or not? So this actually 2 different paradigms for computing. For differential equation model, people also call this as parsimonious model. Why is it parsimonious? Because they have a few variable. Very few variable can tell you a story, right? SIR can tell you a story, which means it's highly interpretable and also generalizable. You think about Newton's law, right? Newton's second law. When Newton noticed an apple drop from the tree, this law, F equal to ma, also can help us to help people to land the rocket into Moon or Mars, right? Because the law is there, is the same, but the different gravity constant, of course, right? And there is almost no data required for the differential equation. No data required. So what is required? You need to require some human genius, right? Someone like Isaac Newton and Einstein to discover, observe those kind of principles. Okay, so how about machine learning model? Is on the contrary, they have a huge amount of data and variable, just like a ChatGPT. They have 1.8 trillion parameters, right? So the SIR only has 3 parameters, right? Think about that, the difference. And this is a black box model. Sometimes it works, some don't. Sometimes the neural network can recognize it's a cat, it's a dog, but sometimes it cannot do anything other things. You do not know how to. This is It's a black box model. Of course, some people are trying to do some kind of interpretation on black box, but basically speaking, it's a black box. And also, it's a data hunger model. Without data, you cannot train your model. So you may notice there is a spectrum here. Small data, lots of physics. Big data, no physics at all, right? We don't know, right? So what happened in the middle? We do have some data. It's hard to say enough. You don't know if you say they have a lot of big data, right? Some data and some physics. I know this could be the disease spread as SRR model, but it's not quite good. We want to learn the model. We want to learn the parameter using our real world data. Is that possible? We have limited data to learn some physics. Okay, this middle part is something I'm very interested in. We want to do some intersection between machine learning and deep learning. Okay, so I cannot skip this page and jump to my work because this is basically how we train a neural network. And basically, in a high level, only 4 steps to train it. So first step gonna be pass your information to your brain. Basically speaking, observe, right? Basically pass the data into the neural network. Neural network have 3 types of layer: input layer, output layer, and whatever in the middle is a hidden layer. So the first step can be forward all the information, all the numbers like this cat. Maybe you can just digitalize and numerize each pistol, and you put in a very long input layer, and you propagate it as a number, as a float number. You propagate it in the system. How you propagate? Just like this, right? You plug in one number here. You just weight is just initial one, just randomly, whatever weight you want. You give it randomly, doesn't care. So B is the same thing. You give output. Output goes in another layer by layer, and you can end up the last one. The last one is your prediction, is Y prime. Second step is you have your Y prime. In the term of supervised learning, I want to compare this cat. Is this real cat? It is, right? I'm going to label this as 1. I want to compare the difference between your prediction and the ground truth. We call this an error. We want this error as small as we can, right? So if the small, which means the model is good. Okay, so how we train it? So in calculus, we know how to find we have a loss function. We try to minimize it, right? We have a loss score. We try to minimize it. How you minimize it? In calculus 1, you know how to find the slope of, the lowest point, right? In calculus 1, you find the slope. If the slope is positive, you move to left, right? If it's positive, you move to left. If negative, move to right. This is the gradient descent, right? So this is we find the minimum point of the function. There is no difference over here. We are trying to use the backward propagation to find the minimum point. We iterate this process until we obtain the lowest score. There's a threshold for that. Or we run out of data. That's we have to solve. Okay. All right. So you can think about you will have the old radio receiver. There are some knobs, right? There's a knob. Right now you can think all the hidden layer as 7 knobs. You turn those knobs. You're trying to find the best frequency. No noise, right? That's the idea. Okay, physical informed neural network. How we add physics here. This study initially started by Neil Ducky in Brown University, and in 2019. Since then, this method is very popular. Application in a lot of different fields, and the idea is very, very simple. So previously there is a loss, right? This loss is because of data, because it's whatever data you give to, right? This is called the data loss. And instead of data loss, he just artificially, virtually add another physics loss. Physical loss depends on the problem. What you also trying to solve is the physical law. And then you just train, use a new particular normal method. Just train with this new additional physics loss. So the analogy I like is I still use a cat, right? This is the data I have, right? I'm going to train this, what is the cat? Instead of the data loss, you also give other information. You give a sketch of a cat. That's the physics. Okay, you tell the machine, okay, tell the neural network, if a graph looks like this, it's probably a cat, right? It's a cat. That's your physics law, physics information. Yeah, loss function as a virtual one. This one does not exist at all. We manually add there. Okay. And the method called auto differentiation. Without this method, the trend cannot be possible. I'm not going to discuss that. And this method going to use less data, smaller neural network, and fast speed, very efficient compared to the original neural network. So actually, Chris and Anthony, they are doing is they use this method to try different system and to find a good parameter, like the super hyperparameter for the neural network, right? To turn those kind of things. Okay, so this is work done by Chris, and this function is a damn harmonic oscillator equation. This equation just modeling this phenomenon of spring, a mass under a spring and up and down. This has been damped. So this is the equation itself, and we basically add a physics loss here. The physical loss, what's the physical loss? It is represented by U theta, which is, you think about our neural network. I want this neural network satisfy our equation, right? I want neural network satisfy our equation. If I go back to the equation, I plug in my neural network here. If this is not equal to 0, this is not a solution. If this is equal 0, it is a solution, right? So, okay, I'm not using my neural network. I plug in over here. This is probably not equal to 0, right? Randomly. So I'm going to minimize the right-hand side by backward propagation. I minimize it, right? Try to make it as small as we can. If this is close to 0, I say this is a solution. It's an approximation solution, which is pretty good, right? This is the idea. We're going to use training a neural network. Here is the analytical solution. This is ground truth. We put into the data loss here, and we also run a physical. This n represents the left-hand side of this equation. Okay. Okay. So we can see that we compare the result from the neural network and the pin. This is neural network, which is traditional neural network without the virtually physical loss. This is the pin. We can see that the blue curve is the model prediction, and the gray curve exact solution, the true solution. The pin behave very well. At least he can, after 3,500 training, this is the solution. After 15,000 training, the solution gonna be, estimation solution gonna be exactly overlapped with the true solution. Okay. However, you use the traditional neural network without physics loss, no matter how many times you train, it always behave far from the truth. You may say, okay, you're from computer science, right? You may say, okay, this one train only have 200 times, 700 times. Why is it not fair, right? Why is this one you try 15,000? It's not fair. It's not a fair game. Actually, you can see this graph because after 300 times, almost the neural network is a traditional neural network is not trainable. It's untrainable because no matter how far you train it, it's the last curve is still level, okay, level, and the pin still could be goes down. If the curve goes down, you want it always goes down, right? Until it's level. So yeah. Yeah. Anthony the work on logistic differential equation. Also have some application in ecology. And basically we use the same idea. I just want to try different equation. Previous one is second order. This is the first order equation. And we can see the result is also pretty good. And Anthony is also work on some PDE, partial differential equation. And the PDE have a far more harder train compared to ODE. And he used, this is Poisson equation. Poisson equation have some application in biology, even some mechanical engineering. To use a package, which is called DBXDE, to do the estimation of the solution. And I'm not going to detail for this. And basically, he used some he tweaked some hyperparameter to make this approximation far more better than previously. Okay, some ongoing research, and you know what's the SIR model, right? So we can add one more compartment and make the model is useless, we want to make it more useful, is we can add one more compartment here. We call that exposed compartment. Basically speaking, this is we add infection. So suspected people want to go to exposed compartment and then move to the infectious compartment. And trying to just split all the population as one more compartment. And I actually I'll be gonna present this research in this year's STARS conference next week, right?
April 2nd week.
Okay, April 2nd week of April. I don't want to spoil your talk, and so yeah, if you're interested, you can attend his talk. But basically speaking, we want to use PIN to learn the infection data to learn the disease transmit rate, like the alpha, beta, and the gamma. Let's use real world data trying to learn what those numbers are. We know that the number have some range from 3 to 8. We want to study more specific at some region what that number really are. Okay, and also we want to select the appropriate hyperparameter to exploit the training. All right, so differential equation plus artificial intelligence is not just a PIN. Okay, so we may have some different ideas. This field have a broad, a diverse research. This is one research I have done with a colleague in computer science department. So we basically use a SIRD model, which is differential equation model, plus a neural network, trying to predict the COVID infection in the first wave in Italy. The data we have here is the infection data from Italian. Each column represents the region or province. I don't know the region for Italian. They have daily infection for this is more than 120 days of data, and the number is the infection on that day. This is a data set, and we are trying to model it. Okay, just like sometimes your model is dictated by the data you have, and just like when you cook the dinner, what's in your refrigerator, right? So the model we have is we don't have the immigration data. We don't have the human mobility data. So whether how human transfer from one region from that other region, there's no way you can track that. So what we do here is we use SIRD. We add one more compartment. We call it the desk compartment, and there is no, as I said, there is no transportation data. So what the idea is for any region, for example, like a LOSI here, we use SIRD model to learn to predict its infection. Okay, SIRD just predict this one section, and this section has how many neighbors? 1, 2, 3, 4, 5 neighbors. I'm going to use a recurrent neural network to learn to study the infection of those neighbors. We don't have data for the transportation, but we do believe their neighbor infection gonna be negatively impact for that region. Okay, for each region we build one model. For each region we build a model, one model. Okay, so this is one of the region we have. This is LOSI here. The idea is it's neighbor regions. We put their neighbor infection number into we call this edge feature. We add one more here. I mean, this infection is by itself. Beta 1 is infection by its location itself. Beta 2 is infection contributed by its neighbors. Okay, and we're gonna use a neural network, which is a recurrent neural network, to learn this IE here.
So that's why you don't have a differential equation for I sub E, right?
Right. So IE represent edge. Edge means his neighbor. Infection with neighbor. We add there because we believe that's going to be a big contribution. We all see that our result actually better. Okay. So yeah, this is a high level. This is what this model is. Okay, let's see the result. And so we compare our result with ARIMA, which is autoregressive integrated moving average. This actually is a benchmark for a statistical model. It's just average in the past 4 or 5 days and and adjust it and then do that again every 4 or 5 days, right? Then on the first column is their prediction. You use the first 80% a day as training data and the last 20 as testing data. We can see that. And just by eye test, right? Just look at the picture. So which we can see that for the lossy area, the model is the curve is more close to the ground truth. The blue is the ground truth. The orange curve is the prediction. It's more close, right? Just by the eye test, we can see it's much better than especially for the Lambodia area. Lambodia is by the way, Lambodia is the region in Italy have a lot of population. Just like just a lot of the population is not evenly distributed, right? So we can see at a lot of population region, this model is much better, outperforming. Okay.
What's your vertical axis again?
Vertical axis is the scale infection rate. Scaled infection rate. Yeah, so for some reason, for the demonstration purpose, we scaled the result. Yeah. But to the comparison purpose, they should be same. Yeah, this is just eye test, right? So we don't just happy with eye test. If you just use your training data, use your testing data to compare with the ground truth, you use the root mean square error. We can see the result is also smaller, right? Our error is a little bit smaller than, sometimes it's far smaller. For the first one, Lambodia, again, with a high population, much better. Yeah, this is error comparison. Any questions?
Can you show the other one, the previous one? Last, okay. Wow.
Yeah. I mean, the first column is ARIMA. This is the ARIMA. And the second column. Okay, so intersection of AI-powered modeling and computing. This is a very promising area. I'm very interested in, and I know some familiar face today. At least 4 or 5 of them.
He's your student.
He's already those pass, right? Yeah. So we are also doing some differential equation plus AI. Gray model is one classic differential equation in engineering, which is studied more than 20 years. And right now we are thinking, how about we use Gray's model and the transformer, which is large language model, right? So whether we can make the predicted better. We don't have a result yet, but we'll see the potential there. Okay. Yeah, and the three of them, and 4 of them actually is working with me right now with Dr. Guo and me. And we also do something like VR in data visualization. And this is also one branch of research we are interested in. So actually, we do have a research hub. This is a correlation between multiple departments and faculty and students. And if you are interested in this research area, and AI or applied mathematics, computational mathematics, just scan this QR code. You will see more information on our this is ISAS research. Okay. Any question?
Can you share a little bit about the electricity consumption research that you're doing on the last slide? Can you share a little bit more detail on that?
Sure. Okay. So Green model basically is an engineering model. Is actually invented by a mathematician in 1982. And after that, there's a lot of engineering. There is more than 20 years of conference actually in that exists. But there is a lot of limitation for that because as you think about 1982 or 1990, last century, the data we collect is very rare. I mean, they may, for the electricity consumption, they may have the monthly data instead right now, we have some sensor, we have the technology to gauge the data in every second, right? So at that time, they only have the monthly data. So the potential there is we want to use this old technology, which is grandpa time series data prediction, right? Plus the transformer, which is the grandson of the time series data predictor, whether there is some chemistry between them, something like that. So one of the idea maybe is we can use the green model to predict the long trend. We use the transformer to find to study the error of the each trending, something like that. Yeah. So yeah, I always want to mingle things together and just see whether we have something. Sometimes, in the most cases, I fail, to be honest. But sometimes we win. That's the joy of the research. Yeah, Dr. Chen.
Yes, I was just wondering because you mentioned, the AI, the term has been around more than 70 years, right?
Right.
But my question for you, I mean, if you look over the AI research today, compared with 70 years ago, do you think maybe to some degree it's like complete different, or maybe even have any connection in the early work still kind of point to the direction, yeah. Historically, to look at the AI concept?
Just like any field or any study, you go back, you will see a lot of, how to say this, you just, a lot of try, just like what I did, lots of try, but it's wrong. Most cases it's wrong. Some is successful. Just think about the backward propagation. Geoff Hinton, the guy who won Nobel Prize last year in physics. Actually, even in 1903, his research is not popular at all. He have no money to travel, actually. And then not few people do the neural network work because there is a lot of limitation. It's not, you don't have data, you don't have training, you don't have the result like ChatGPT right now. So people think this is not useful. Especially for pure math people, they don't think this is more like a toy, just computer science people play with. It's not very serious mathematics. So he don't receive the fame right now. Okay, so you think that way is when starting with AI, I think from the symbolic AI, is just use a mathematical notation, just like to argue, and then it's have a lot of limitation, and then to expert system is just feed the AI some knowledge, AI as financial knowledge into the system, but only can be good for certain things, not like AI, more like can solve the general question. So yeah, I'm not sure I answer your question, but if you go back 70 years ago, just like any research or any subject, so it's a randomly, right? It's a random walk. So it's hard. Yeah.
And I'd like to follow up on that. I guess today one of the big difference will be the investment. The investment now is almost totally coming from industry. Think about last year, OpenAI, they earned like $3 billion and they still post a loss of $5 billion. Microsoft at this point is pledged to spend another $44 billion to OpenAI in the next 5 years until it will break even. Of course, maybe tomorrow they change their mind, but this is kind of the investment that we're looking at, which 70 years ago, there was only
7,500.
But the speed and the focus is just way, it's like crazy. Not for that we have seen that anywhere, any close.
If that's the case, do you think probably there's no third winter for AI?
Yes.
I talked about with multiple people. Do you think there is any winter in the future? I don't think so. So actually, you say winter, yeah, because everything can build up on AI. I think that's way, but you can, yeah. Just like my human extension. I have to have a research assistant with me, AI research assistant, to make things better.
Guess what you will see is that it becomes normal. Just like you don't think about social media and email as something that is so hard. You just, you can't live without it. But it's everywhere. instead of that, that excitement that we see.
I agree. Yeah.
And you can put your CV, you can put on your CV, I know how to use email. It doesn't work.
Fun. Right now, you still can train your network in the CV, right? But 10 years later, okay, don't do that. Yeah. Everyone can do that. Okay.
Any question for online? I think they still have 11 people.
Oh, sorry.
Yeah, maybe you can ask.
Yeah, no question, I believe. Yeah. Nope. Okay. Okay. Thank you for coming. Okay, guys.